In this chapter, we're going to look at amines. Now, amines are derivatives of ammonia. So ammonia is a nitrogen with 3 hydrogens around it, NH3, and all we're doing is we're swapping out those hydrogens for alkyl groups. So it's kind of like how alcohols are essentially just water, where you've swapped out a hydrogen for an R group, right? Here it's a similar case. Now, depending on the number of alkyl groups you swap out, or the number of hydrogens you swap out for alkyl groups, you can have a primary, secondary, or tertiary amine. All right, now it's possible to add a fourth alkyl group, and now you've got an ammonium ion, a tetraalkyl ammonium ion. But looking at just the neutral versions of this, we have primary, secondary, and tertiary. Okay, you've probably remember those terms for alcohols as well, except in the case of alcohols, the alkyl groups are attached to the alpha carbon, so not on the oxygen of our alcohol, obviously. All right, so the nitrogen on our amines, of course, are going to be trigonal pyramidal, right? To meet the octet rule, we've got a lone pair on that nitrogen. Keep in mind that nitrogen also is relatively electronegative, not as much as an oxygen, but more than carbon, obviously. So your nitrogen is generally an area of high electron density, and that's where a lot of the chemistry happens, I guess. So that lone pair in your nitrogen will act either as a nucleophile or as a base, either to do a nucleophilic attack or to pluck away a proton, form a nitrogen-hydrogen bond, and make an ammonium molecule, ammonium ion. Right. So again, it depends on the situation. So here you can see in this first example, this nitrogen picks up that proton, and we get the corresponding ammonium chloride. Over here, you can see that it basically does an SN2 mechanism and kicks off that chloride leaving group, again making an ammonium chloride. So again, it's a very similar function, but the question is, what is it doing, right? So let's talk about naming these. With primary amines, you can just treat the amine as the root word and add on the alkyl group as a prefix. All right, so you look at the the alkyl name and just add amine to the end of it, right? So for example, here we have ethane with an amino group coming off, so that's ethylamine. Here we have an isopropyl group. Again, notice that we're using kind of the common name there, and that's okay. Here we have a cyclohexylamine as well. Okay. That being said, with the IUPAC naming, you want to try and basically take the alkane name and swap out the E for the word amine. Okay, now here you want to have a locant, of course, because it need not be on the number 1 carbon, and accordingly you can number your locants for your other substituents as well. Okay, now in that example, the amine was the primary functional group, so that's why we had amine at the end there. However, that might, you need not necessarily have your amine taking priority. So if there's a higher priority group, you treat your amine as a substituent, and so you use the prefix amino there, okay, instead of the root word amine at the end of the name. Okay, so here are examples where we've got example here, this alcohol group takes priority, so that alcohol group's in this number 1 carbon, so 1, 2, 3, 4, so that's a butanol, and that amino group is on the number 4 carbon, so it's 4-amino-butanol. Okay, likewise here we have a benzoic acid, and that amine group is para to that benzoic acid group, or the carboxylic acid. So you could also call this 4-amino benzoic acid, right? Because that's, if you use a numbering system, that's 1, 2, 3, 4. Okay. Now, if your amine is on a benzene and it's the kind of main priority group we're looking at there, aminobenzene is known as aniline, so you can use that as the root word. All right, so even when you have other substituents, you can say that amino group's at the number 1 position and number things accordingly. So here we have a chlorine that's, the 3 position or the meta position. So it's 3-chloroaniline or metachloroaniline. Likewise, here we have multiple substituents. If we go counterclockwise, that fluorine's at the number 2 position, and that ethyl group over here is at the number 5 position. Okay, so it's 5-ethyl-2-fluoroaniline. Again, you've got to put these in alphabetical order. Okay. Now, when it comes to secondary amines, if we use the common naming system, you now have multiple alkyl groups. Actually, it looks like we've got a combination of secondary and tertiary amines here in these examples. But basically, you just list out the alkyl groups in alphabetical order. Okay, so for example, here we have a methyl group, an ethyl group, and a propyl group. So putting that in alphabetical order, it's ethyl-methyl-propylamine. Okay, now if you have multiples of the same alkyl group, you can use the prefixes di or tri. All right, so or in the case of an ammonium ion, you could even use tetra if that's the case. But yeah, so over here we have a secondary amine where both of our alkyl groups are ethyl groups, so you call that diethylamine. Here we have 3 methyl groups for this tertiary amine, so it's trimethylamine. Okay. Again, though, this is the common name, right? If we're using IUPAC, you have to look at the other alkyl groups as substituents on the nitrogen of the main, the amino group that's on the main parent chain, right? So, in other words, you look for your main alkyl group or your main carbon chain that has the nitrogen attached to it. Okay, and you name that accordingly. Name it just as you would any primary amine. The only difference now is you've got these other smaller alkyl groups on your nitrogen, and so you list them out as substituents, but the locant here is going to be an N, okay, to show that they're attached to the nitrogen of your amino group and not to the parent chain. Okay, so while we use numbered locants for all other substituents, it's just those alkyl groups that have to have that N in front of them. We saw something similar to this when we were naming amides, a couple of chapters ago. Okay, so let's practice this. Go ahead and try naming this secondary amine. You probably want to use the IUPAC system here, because I think given that this is not a simple cyclohexyl group, you can't simply call this, cyclohexyl isopropylamine. Okay, so if you pause this and come back, there's the name of this. You may have left out the stereochemistry, so please note that these are chiral centers, so which is why the Kahn-Ingold prelog prefixes are given here. All right, so this is going to be our parent chain, the cyclohexane. Okay, so this is cyclohexanamine. Right, you swap out the E for amine. Okay, that amino group is automatically at the number 1 position, so that methyl group is going to be at the number 2 position. So I would say you could probably have left this one out of the name. I think it's understood when you say cyclohexanamine that the amino group's at the number 1 position. All right. Anyway, so if you left out the 1, I think that would still be correct. And of course, if this was just NH2, if this were a primary amine, you would just call that 2-methyl cyclohexanamine and be done there. But here we've got this isopropyl group as that alkyl group that's attached to that nitrogen to make it a secondary amine. And so the locant there is the N for the nitrogen. Okay, so let's talk a little bit about the properties of amines. We have seen that that nitrogen is trigonal pyramidal. Thing to keep in mind here is we have an sp3 hybridized orbital here with that lone pair housed in an sp3 orbital, and so as an sp3 hybridized atom, which has sort of tetrahedral geometry, right? If you're looking at electron pairs, that bond angle is somewhere in that ballpark of like 108, 109 degrees, right? It turns out the bond angles between the carbons is a little bit smaller than 109.5 because the repulsion with the lone pair kind of squeezes them closer together. So that's why this angle is 108 instead of 109.5. Okay. Um, in terms of bond lengths, your carbon-nitrogen bond lengths are a little bit shorter than you would expect for a carbon-carbon bond. Remember, your nitrogen is smaller than a carbon, right? So, that bond length is going to be shorter accordingly. A quick note here about that hybridization. We saw this back in the chapter on aromaticity. Remember, if that nitrogen is going to be involved in a conjugated pi system, we need an empty, or well, not an empty p orbital, but an unhybridized p orbital to get involved there. Now, sometimes, so the nitrogen would have to be sp2 hybridized, and sometimes this can include the p orbital housing that lone pair, right? I think we've seen this in kind of the difference between pyridine versus pyrrole, right? Why one of them is more acidic than the other, or more basic than the other, rather. Anyway, so it's something to keep in mind when you're looking at that, that hybridization of that nitrogen and what that lone pair is doing. Okay, so that's something we've seen before in a previous chapter. So, brush up on that accordingly. Okay, so regarding the chirality of your amine, right? If you have three different alkyl groups on your nitrogen, and your lone pair obviously is different from atoms, you might think, well, that nitrogen's chiral then, right? Its mirror image would not be superimposable, right? It would be the enantiomer. However, you have to think of your nitrogen here kind of similarly to how we think of radicals or carbanions or even carbocations. Well, carbocations are a little different; they're kind of flat. But in the case of your these other examples, remember, even though those are trigonal pyramidal to a certain extent, they are capable of of an inversion, right? And therefore, your optical activity kind of gets muted. It gets canceled out because it's relatively easy to flip from one quote unquote enantiomer to the other, right? Going through this trigonal pyramidal, this sp2 hybridized intermediate, or not intermediate, sorry, transition state. All right, so I mentioned earlier that nitrogen's relatively electronegative, not as much as oxygen, but decently electronegative. If you brush up on some of the stuff we learned in Gen Chem, you'll remember that nitrogen, along with oxygen and fluorine, is electronegative enough to allow hydrogen bonding, right? So we kind of see this even with physical properties like solubility and melting and boiling points, right? Your nitrogen is capable of hydrogen bonding, which means it is soluble in other solvents in solvents that have hydrogen bonding, like water, for example. Okay. Now, a little note here. Of course, we're dealing with organic molecules, so you have to hope that the alkyl part of your amine is fewer than 5 carbons. Once you start getting to larger and larger alkyl groups, the non-polar regions, the low polarity of those groups kind of take over, and you start finding that your amines get less and less soluble in water. Okay, so you need fewer than 5 carbons for your amine to be water soluble. Okay, we can see also the effect of this in boiling points here. You can see that, for example, if we compare, propane to ethylamine to ethanol, notice that your amine is a much higher boiling point compared to the nonpolar alkane, but significantly lower than the very polar hydrogen bonding we see in ethanol. Okay, though again, keep in mind that your amine can also engage in hydrogen bonding, just not as strongly as your alcohol does. Okay, we can see here also with the propylamine versus ethyl methylamine and trimethylamine. All of them have the same molar mass; they're isomers of each other. But you can see this tertiary amine has a significant drop in boiling point. Please note that tertiary amines can't engage in hydrogen bonding. They don't have a hydrogen attached to that nitrogen. Okay, so propylamine and ethylmethylamine both have much higher boiling points compared to your trimethylamine. Okay, so again, something to keep in mind when you're looking at your amine and trying to predict its physical properties. Okay. Other physical properties of amines. Amines tend to be, well, stinky, right? There are a lot of, like, not nice smelling amines. You can see in the case here of putrescine and cadaverine, very inventively named compounds, and you can imagine why they've got those names. Um, yeah, so let's look at some more chemical properties, right? We generally have explored acid and basic properties of a lot of the molecules we've looked at. And I've pointed out earlier in this chapter that amines, like ammonia, are basic, right? That nitrogen can act as a nucleophile, but can also act as a base. All right. So generally speaking, amines are stronger bases than alcohols and ethers. If you think of the A in ARIO, in terms of qualitatively assessing acids, remember, nitrogens are less electronegative than oxygen, right? So that nitrogen is going to be less acidic and conversely more basic than your alcohol or ether. Okay, so as a result, amines can be readily protonated by strong and weak acids alike, because the resulting ammonium ion is decent enough, is stable enough at holding that positive charge, and this equilibrium is shifted to the right. Okay, so if you want to put a ballpark pKa on that, somewhere around a pKa of 10 for that ammonium ion. Okay, so obviously your carboxylic acid here is a much better acid, and that's why this equilibrium is kind of shifted to the right there. Okay. So notice that in all of these examples we have that ballpark of about 10 for the corresponding ammonium ions for all of these amines. So it's something to keep in mind when you're trying to qualitatively determine, what's going to or rather quantitatively determine what's going to protonate these amines. Okay. Once we start getting into get away from aliphatic amines into these aromatic ones, notice that now your charge can be kind of delocalized for your your lone pair can be utilized in the resonance structures of your deprotonated version of your amine. So as a result, the protonated version is a little bit less stable, right? It no longer has that lone pair taking part in that delocalization. So as a result, the pKa of that protonated ammonium ion is a little bit lower, right? This really wants to return to its neutral state that can engage in resonance structures, and therefore, that's why we see these lower pKa values. Okay. Pyrene and pyrrole and pyridine, I think we've talked about that already. I alluded to it earlier when I was talking about the role of of that nitrogen being sp2 hybridized and the role of the lone pair, which may or may not be the case. Just to jog your memories really quickly, pyridine doesn't need that lone pair for aromaticity. It already meets Huckel's rule with all of these pi electrons. So since that lone pair is not involved, it's free to pick up a proton. That being said, for pyrrole, that lone pair is needed for aromaticity. So the resulting ammonium ion is very, very acidic. It really wants to go back to the aromaticity of the neutral molecule. Okay, and that's why you can see this pKa is really, really low. All right. I mentioned earlier that neutral amines generally are slightly soluble in water, but keeping in mind that amines are basic and you can, essentially do an acid-base reaction with them, well, you make the corresponding salt, right? And remember, these ionic compounds are, have much better water solubility. So if you do want to make an amine more soluble in water, typically the way to do it is to react it with an acid, and it will go into your water layer much more easily. All right, we've taken a similar approach with carboxylic acids, right? We've seen that reacting them with bases and turning them into salts that way also makes them more water soluble. So similar approach here, except you obviously need to use an acid. Okay, I think I pointed out already that the your pKa's of your your aliphatic, your regular alkyl amines, of those ammonium ions is somewhere in that 10, 9, 10, 11 ballpark, whereas it drops significantly for aryl ones. One thing to notice here is the effect of electron donating, electron withdrawing groups, right? So notice that an electron donating group here, like methoxy, generally increases your pKa, right? It's pushing electron density towards that, that positively charged nitrogen, stabilizing this ammonium ion. Okay, so that makes it less acidic. It feels less urgency to get rid of that proton. Okay, whereas if you have an electron withdrawing group, notice that it has the opposite effect, right? It's pulling electron density away from that nitrogen, making it feel that positive formal charge even more starkly. So it really wants to get rid of a proton to go back to the more stable, neutral amine here. Okay, so that's why its pKa drops so significantly. Oh, quick note here about this last question, because that's, I think, a pretty important one. Amides are not as basic. They're generally not basic. Remember the nitrogen in your amide is attached to a carbonyl group, so that lone pair is involved in resonance with the carbonyl, with the pi electrons in your carbonyl. So if you protonate that nitrogen, it can't do that anymore, right? So generally speaking, your nitrogen and your amides are not particularly basic. Okay. Again, pyridine and pyrrole, I think I've already talked about that. Again, it comes back to Huckel's rule and the involvement of those electrons on the nitrogen with the conjugated pi system in pyrrole. Okay. Um, I think we talked about this back with carboxylic acids, but this is getting into more of a Gen Chem application. But amines being weak bases can also be, and the ease at which you can turn them into an ammonium salt makes them good candidates for making buffered solutions. So we're not, if you do want to calculate the pH of a buffer, you can use the Henderson-Hasselbalch equation as we've seen here. Again, I'm going to gloss over this because this is, I said, more of a Gen Chem problem. Okay, so yeah, again, if you want to practice this, so let's say we've got the pKa of your ammonium ion is 8.3, and you want to get a pH of a particular thing, you can solve for the ratio of your amine to the ammonium ion. Okay, let's get into the chemistry, the synthetic methods involved with amines. So first, let's talk about how to make amines, right? And we've seen this quite a bit in previous chapters, right? At this point, where we're getting towards the end of, of our regular organic chemistry before we start getting to some biochemistry. So at this point, you've probably seen, you've seen all these other functional groups, and you've seen a lot of chemistry. Yielding various products. So we've seen some ways to turn nitriles, for example, into amines by reducing them, right? So you can see here we can add on a nitrile group relatively easily using cyanide as a nucleophile, and then we can just reduce that using a reducing agent like lithium aluminum hydride. Okay, and of course, this is also a great way to add to your carbon skeleton because the carbon in your nitrile group has extended your carbon skeleton from your original molecule. Okay, we've seen that we can convert carboxylic acids or acid chlorides into the corresponding amides, right? So you can see here in this first step, we've converted carboxylic acid into an acid chloride. We're basically swapping, by using thionyl chloride here, we're swapping out that OH group for a Cl, okay? And then we can use ammonia as our nucleophile, kick off that chloride leaving group, and now we've made this amide. Again, just like with our nitriles, we can reduce that down to the corresponding amine. Okay. In terms of aromatic, amines, so if you want to try to make aniline, a good intermediate here is a nitro group, right? We can add on a nitro group using concentrated nitric and sulfuric acid, right? And then we can just reduce that either using hydrogen over a platinum catalyst, or we can use a metal reducing agent like iron, zinc, tin, or even a tin chloride, tin 2 chloride, and in the presence of some acid, and it will reduce down to the corresponding amine. Okay. Oh, quick note here. Out of these two methods, I think when we talked about aromatic compounds, we kind of focused on this one. You can reduce this with hydrogen, but typically you need a higher temperature and a higher pressure of hydrogen to get this to work. So depending on what other substituents you have in your benzene, this might not be the best way to go. You might wind up reducing other groups that you don't want to. So typically using the milder metal reducing agent is usually the way you want to go. Okay. All right, so let's look at some new methods. Ammonia, as we've seen, the nitrogen in our ammonia and amines is nucleophilic, so we can add on alkyl groups through a simple substitution reaction. Okay, so you can see here if we use ammonia as our starting material and an alkyl halide, we can kick off that halide ion and make the corresponding ammonium. Okay. Now remember, you've got ammonia present as a base, so this can be easily deprotonated to the neutral amine. Okay. Now that being said, it's really hard to stop at just one alkyl group. You tend to do a poly substitution, and this will keep on going until you have the tetraalkyl ammonium salt. Okay. Another way we can do, we can make a primary amine is to use sodium azide. So the azide ion has 3 nitrogens in it with a -1 charge. Okay, often present as a sodium azide. This is a very reactive material, as you can imagine. But the azide ion is a nucleophile, so you can swap out a halide, using that reagent. You'll get sodium halide as the byproduct. And then this being so reactive is easily reducible to the corresponding amine. Okay, let's have a look at the mechanism. So here's your azide ion. Okay, you have that act as a nucleophile. So that nucleophilic substitution is pretty straightforward. You kick off that halide leaving group. Now out of this resulting product, okay, this is a Zwitter ion. Like I mentioned earlier, this azide group is not particularly stable, so it reacts pretty readily. So we have our reducing agent, in this case lithium aluminium hydride, providing a hydride ion to that nitrogen. Okay, so that should be a nitrogen there. I don't know what went wrong with that slide, but anyway, so that hydrogen comes in there and makes this a negatively charged ion. So we can have these electrons, move accordingly, and you wind up breaking this bond. So this nitrogen winds up having a negative charge, and you lose. You're forming a triple bond between these two nitrogens, which is nitrogen gas. Now this is great because remember, nitrogen gas will just bubble away. The reverse reaction can't happen because you're losing the nitrogen gas. Okay, so this pretty readily proceeds to this product. Of course, this is a charged product, and it can really easily pick up a proton to make the neutral amine as your product. Okay, another method to make an amine is called the Gabriel synthesis. Okay, so first you take thalidomide and convert it into potassium thalidomide using potassium hydroxide, right? So you've got this charged nitrogen species here, and it's that negative charge is resonance stabilized. This is a nucleophile that can kick off your if you react this with an alkyl halide, it does an SN2 reaction, kicks off your halide, and you get potassium halide as a byproduct. And you can see here how we've substituted on that alkyl group to the nitrogen. Okay. Quick note here, this works best through an SN2 mechanism with a primary alkyl halide. If you use a tertiary alkyl halide, given how bulky this is, it's going to act more like a base than a nucleophile. So if you use a tertiary alkyl halide, you'll probably wind up getting the elimination product, which isn't what you want, obviously. Okay, so once you've got that alkyl group substituted onto that nitrogen, you can accordingly, just react it either with an acid to get the corresponding ammonium ion, or with hydrazine to get the corresponding neutral amine. Okay, but basically that alkyl group that we added on from our alkyl halide is now attached to a nitrogen as either a primary amine or a primary ammonium ion. Okay. Another method that we've seen before is to go via an imine. So we've seen that we can convert a ketone to an imine relatively easily using ammonia, right? If we use a primary amine, of course, you'll go through the enamine. You'll form an enamine instead of an imine. But anyway, so you have an imine here. You can then reduce that accordingly to the corresponding amine, right? Essentially, you're just adding hydrogen across this double bond. Just like adding hydrogen across a carbonyl double bond would reduce this to an alcohol, doing that to an imine will reduce it to an amine. Okay. Oh, and by the way, this can be done in situ, which means it can be all done, in one pot. You don't have to isolate the amine. You can, make this and then just, pass it over your platinum catalyst with hydrogen. So we call this a reductive amination, right? We're essentially converting our ketone to an amine. We're reacting with ammonia or an amine to do that. And then we're reducing it using some reducing agent down to the corresponding amine that we want. So hence the name reductive amination, which, autocorrect when you try to write this out is going to be a pain because they'll keep on wanting to change this to animation. But anyway, now here you notice we are using hydrogen with a platinum catalyst as a reducing agent, and I've pointed out where that this can sometimes be a little harsh, and we want to try and do this a little bit milder. So another alternative is to use sodium cyanoborohydride. Now, we've seen sodium borohydride as a reducing agent, right? This is a milder version of lithium aluminium hydride. Sodium cyanoborohydride is also, makes it even more selective, right? That nitrile group is electron withdrawing, and so it kind of stabilizes that negative charge on that boron. Okay, so now that being said, you can depend. We used ammonia in our first example, and we went, through that imine intermediate and made the corresponding primary amine. But accordingly, you could use a primary or a secondary amine instead of ammonia and make the corresponding secondary or tertiary amines. Okay, so that's something to keep in mind. Okay. Oh, this is a good question. Why don't we use sodium borohydride? Again, we want the cyanoborohydride to basically reduce the product of this reaction, right? And if we're doing this all together, sodium borohydride is going to reduce your ketone down to the alcohol. Okay, whereas your cyanoborohydride is a little bit more selective for the imine or enamine. Okay, so here's an example of a tertiary amine. Let's go ahead and design a synthesis for it. So pause this video, and when we come back, we'll go over the answer. Okay, so if you've returned, let's look at the answer for this. So if you're looking at your final product, you notice that these two. This is a tertiary amine with these two alkyl groups kind of attached together. We've got kind of a cyclic part of this molecule. So it makes sense that when you're doing this, you want these to be together. You want to maybe start off with an amine that has, that's a heterocycle like this, and that's the case here. We start off with a carbonyl that has the rest of the molecule, and we're going to use this secondary amine to tack on here. Okay, and that's kind of what happens. We, use this nitrogen. We're going to swap out this nitrogen for this oxygen and reduce it accordingly to the corresponding tertiary amine that we see here. All right, so let's go over these new reactions we've learned for converting to form an amine. So we've seen that we can use potassium thalidomide Say that 10 times fast, right? So basically, the Gabriel synthesis, you can use that with an amine. Like I said, this works best with a primary amine, so you don't want to go beyond that because you'll get the elimination byproduct. And then you can use a hydrazine to make the corresponding primary amine. Okay, though of course, as I've pointed out, you can also you can go to the ammonium ion accordingly too if you use an acid. With sodium azide, you can of course use that azide ion as a nucleophile and then reduce it accordingly to your primary amine. And then you can do the reductive amination using a carbonyl, convert it using ammonia to make the imine, which you can then reduce using the very selective sodium cyanoborohydride. Okay, and those were primary amines. Of course, if you want to make a corresponding secondary amine or tertiary amine, you can accordingly use your reductive amination. Right? In the previous slide, we used ammonia as a starting point, and that's going to give us the primary amine. If we use a primary amine instead, we would get a secondary amine. If we use a secondary amine instead, we get a tertiary amine. Okay? Now, your tertiary amine is still nucleophilic, so it is possible to tack on an extra alkyl group and get the corresponding ammonium ion. Okay, so here's an example of a tertiary amine. Go ahead and design a synthesis for this starting with things that have 6 carbons or fewer. Please note that that's 6 carbons, so it's okay to have your amine with 6 carbons and the nitrogen. Okay, so I kind of point this out because notice that one of our groups is a benzene ring, which has 6 carbons. And so the fact that the nitrogen's on there and you're probably not going to do a nucleophilic attack or nucleophilic substitution on a benzene means that you probably started off with some form of aniline. Okay, so if you've paused this video and come back, here's a potential answer. So here you can see that we can do a reductive amination using aniline as our amine. Okay, so that's a primary amine with this aldehyde that provides this alkyl group. And then subsequently, we can add on that ethyl group by, the secondary amine that we make is nucleophilic, so we can just do a simple, nucleophilic substitution, kick off that bromide leaving group, and tack on that ethyl group accordingly. Okay, so making amides, we've seen that we can tack on, an amine or ammonia to a carbonyl using an acid chloride, right? And make the corresponding amide. So that's the case here. To do this, of course, you are going to need a base, and so having 2 moles of amine is going to be useful for, the second mole winds up acting as a base to help deprotonate the intermediate that yields the final product. All right. Your amides are generally less reactive than acid chlorides. We've seen that back in the chapter on carboxylic acid derivatives. So we're not going to see a polysubstitution on that nitrogen. Okay, so as a result, because polysubstitution is not likely, you can use your acyl group as kind of a protected group to kind of stop your nitrogen from reacting further. That nitrogen now is no longer going to be basic. It's going to be not very nucleophilic either. Okay, so yeah, that's basically a great way to protect that nitrogen. Okay, so let's have a look. Here we've got a aniline, and we want to make this corresponding bromo product, para-bromo product. So how would we do that? Well, the key problem you're going to run into here is that you can't stop at the one bromine. You're going to have a polysubstitution here. You're going to wind up getting multiple bromines added on. So we need to think about how to avoid this happening. So one way to do this, to make that amine less electron donating, less activating, is to first convert it into this corresponding amide. So we add on this acyl group using our acid chloride, and then we do our bromination, right? It's still, para-directing here, ortho-para-directing, so it's that bromine still winds up in that position. Moreover, because of the bulkiness added to that group, it selectively goes to that para position as opposed to the ortho positions. And then we can reduce that amide back down to our amine. Okay, and in doing so, there's our final product. So again, we can't just directly add bromine to this reactant because we won't wind up with just the one substitution. Okay. Now, downside here is to hydrolyze that amide using an acid or base can be relatively harsh. It involves high temperatures. So depending on what other substituents you have in your benzene ring, that may or may not be, a good way to go. If you want to do a Friedel-Crafts reaction, if a Friedel-Crafts alkylation or acylation, um, you have to first react with aluminum chloride. But the problem with this is that that takes up the lone pair in that nitrogen, right? So you form that complex with the aluminium, and that lone pair is no longer available to activate the ring. Your amine is no longer an activating group at all. Okay. So to get around this, we again can, go via that acyl route. So for example, here, if we convert that amine into an amide, this is still an activating group. Granted, it's not as activating. It's a little bit of a milder activating group, but it's still an activating group. It's still an activating group and therefore can undergo Friedel-Crafts alkylation, okay, or acylation as the case may be. But in this case, it looks like we're doing an alkylation here. Okay, so you see that this methyl group from our methyl chloride, from our chloromethane, is selectively going in that para position. Okay, and then once again, we can hydrolyze that amide back down to the amine to get the product we want. Okay. The Hoffman elimination is another reaction we can do here. It allows us to create an alkene using our amine here. So we're going to basically try to do an elimination reaction and turn this carbon chain here, the parent chain, into an alkene. The problem here is that an amine is not a good leaving group, right? This is, the corresponding negative ion here, the amide ion we would get from this, of course, is very reactive, and that reverse reaction, is more likely to predominate, right? This is not going to leave as a leaving group. So what we can do instead is we can do a polyalkylation of our amine, right? So that works as a nucleophile. We react it with excess methyl iodide, and we add multiple methyl groups to it, right? Basically turn it into an ammonium ion, and now we've got a great leaving group. Okay, this positively charged nitrogen is primed to leave as a neutral tertiary amine. Okay. So what we do here to encourage this is we take this and react it with silver oxide and heat it up with silver oxide. So we precipitate out silver iodide, right? We get rid of that iodide ion as silver iodide, and we have the corresponding hydroxide instead. Well, hydroxide can act as a base, and so it removes a proton from a neighboring carbon and kicks off that leaving group. So you're doing an E2 elimination, in other words, right? That base kind of initiates things, and we make the corresponding alkene. Now, notice that we've made the Hoffman alkene, right? The less substituted alkene instead of the Zaitsev alkene, right? Notice that the hydroxide removed this proton and not one of the protons here that would have made the Zaitsev product. Okay, so why is that? Let's have a look at our Newman projections and see if that explains what's going on. Okay, so over here, if we were looking down at this bond and looking at the hydrogens on this carbon that would yield the Zaitsev product, we could see that the if we look at our anti-periplanar or anti-coplanar proton that would be required to be removed to do this E2 elimination, that bulky alkyl group that forms the rest of the molecule has a gauche interaction with that bulky ammonium ion, right? And that's just less favorable. Okay, now if we look at the bond this way, right? If we were eliminating one of these hydrogens, notice that since these, both of those bulky groups are in the same carbon, we no longer have that gauche interaction between them. We can eliminate one of those hydrogens that's going to be anticoplanar, and we don't have to worry about a gauche interaction. All right, so that's from an electronic standpoint. Well, I guess a steric standpoint. That's why the Hofmann elimination products are preferred over the Zaitsev product. Okay, so from a regiochemistry standpoint, this is very useful for encouraging that Hofmann product. All right, so go ahead and let's try this out with another example. So here is a secondary amine. We're going to react with excess methyl iodide and then subsequently with silver oxide. The formula, and that's wrong, that should be Ag2O. But anyway, silver oxide, and go ahead and predict the Hofmann product. Okay, so there are your products. If you look at your alkyl group on your nitrogen, obviously this is secondary amine, so there's two groups on here, but we're not going to, we're not going to eliminate anything on this benzene ring, right? So it's this alkyl chain that gets converted into the corresponding alkene, and it's specifically, between these two carbons that we form the alkene. That's our Hofmann product. We don't form the double bond here. That would be the Zaitsev product, which we've just seen is, less likely to form under these conditions. Okay, so there's the alkene we form. There's the resulting ammonium ion that leaves as a tertiary amine, right? So, when we break that carbon-nitrogen bond, notice the nitrogen becomes the neutral tertiary amine. Note that it has these two methyl groups on it that come from the methyl iodide. And of course, don't forget, you're going to make silver iodide and water as byproducts as well. If we react sodium nitrite with an acid, we can basically make nitrous acid, right? Now, nitrous acid can be protonated to then yield the nitrosonium ion, right? So we can eliminate one of the oxygens, protonate the nitrous acid, eliminate water, and make the corresponding nitrosonium ion, which you can see here is resonance stabilized. All right, now this nitrosonium ion is very electrophilic. Okay, so it's very reactive with a nucleophile, like an amine, for example. So it will readily react with it, and let's have a look at what we make here. Basically, our amine will attack the nitrogen of our nitrosodium ion, okay, and it will, that will be, the resulting molecule, the resulting species will be deprotonated, and you can see that we've got this neutral product here. Okay, now this is with a secondary amine. If we try this out with a primary amine, we get a much different product. Okay, with a primary amine, we, when we do this, the same process, we get a similar product here, right, with, of course, a hydrogen instead of another R group. But then this subsequently reacts. Basically, you start off by protonating this oxygen, right, and then deprotonating the nitrogen. Okay, you protonate the oxygen again, and now you've got a good water leaving group. All right, and so when here you've got that leaving group, it leaves, and now we've got what's called a diazonium salt. Okay, and this is a great leaving group for tacking on another functional group to our alkyl group. Okay, so from a synthetic standpoint, right, we can convert our amine into this diazonium salt and very readily swap out that original amine for some other functional group. Okay, now in the case of our R group being an alkyl group, these are very, very reactive to the point that it's just not practical. Their explosion risk. Again, this diazonium salt is readily able to react. That diazonium leaving group is great. Really wants to leave as a nitrogen molecule, right? So it really wants to do that forward reaction. So it's actually better, a little bit more practical to use aryl groups, to use aromatic R groups as basically use an aniline derivative. The positive charge is muted a little bit by some of the electron density, by some of the resonance structures with that benzene ring. All right, so that's a little bit more stable, and therefore this last step is a little less explodey. So basically, what we can do with our diazonium salts then is what we call the Sandmeyer reaction. We take that diazonium salt, we react it with a copper halide or a copper cyanide, and we make the corresponding, basically halobenzene or benzonitrile. Okay, so please note that these all have copper in the +1 oxidation state, right? So it's copper 1 bromide, copper 1 chloride, and so on. Okay. Other reactions we can do once we have a nitrile group in place, we can convert that into the corresponding carboxylic acid. So here we've started off with cumene, right, with isopropyl benzene. We can, in this first step, we add on a nitro group. Okay. We can then, convert that into amine in the next step. We reduce that with a metal reductant there. We make the aniline, right? So we have an NH2 group here after that second step. And then we can react that with sodium nitrite to convert that into the corresponding after the third steps, when we convert that into a primary amine. But anyway, with that fourth step, we can turn that into the diazonium salt, as we see here. All right, chloride is the counter ion that stabilizes that a little bit. And then in the Sandmeyer reaction, we take copper 1 cyanide, and we basically swap out that that CN nitrile group. We substitute that in there for that diazonium ion, and so then we have a nitrile group there, which we can then hydrolyze into this carboxylic acid. So notice that we've started off with this relatively unreactive, benzene derivative, and we've converted it into a corresponding carboxylic acid, a benzoic acid. All right. Another reaction we can do is the Schimann reaction, which involves, swapping out our diazonium ion for a fluorine. So you notice that, if I go back a slide, we've had all of the other halogens, right? Chlorine, bromine, iodine. We can't use copper 1 fluoride to do this, but instead, if we use fluoroboric acid, HBF4, that will essentially accomplish that. Okay. Okay. Other things we can do with our diazonium salts: we can heat them up with water, and that converts them into the corresponding phenol. Another method to get rid of that group entirely, just to swap it out for a hydrogen, is to use hypophosphorus acid. Okay, and that'll get rid of this group. Now, if that seems kind of silly, keep in mind that having that amine might be there, initially might be useful from a directing standpoint. So maybe you want that amine as an orthopara directing group, and then you want to get rid of it once you've put in whatever substituents you need. Okay, so anyway, to get rid of that amine, you convert it to a diazonium ion and then treat it with hypophosphorus acid, and you basically get rid of it and just swap it out for a hydrogen. Okay, now if you have a basically an activating group on a benzene, all right, you can do a reaction with your diazonium salt called azocoupling. All right, so essentially your benzene, your activated benzene is your nucleophile here that takes on basically it attacks the nitrogen of the further away nitrogen of your diazonium salt, and it has this dinitrogen bridge that it forms between your two benzene rings. Okay, Now, this goes through an EAS mechanism, so it goes via sigma complex, like we saw back in our, on our chapter on EAS reactions. So, if you want to see what that looks like, here are all the resonance structures. So you can see how we've got this huge conjugated pi system between our two, between our two benzene rings, right? The nitrogen linking the nitrogens linking these two benzene rings are themselves sp2 hybridized, and so they're able to sort of really delocalize that positive charge and make the sigma complex very, very stable. All right. Now, if you remember from the chapter on aromatic compounds, towards the end of that chapter, not on aromatic compounds, on conjugated pi systems, we talked about how large conjugated pi systems lead to colored compounds. And that's the case here. These products of these azo-coupling reactions are what we call azo dyes. They have very bright, vivid colors oftentimes. So just changing the substituents accordingly changes the wavelengths that they absorb and therefore the color that they appear to be. Okay. All right. Nitrogen heterocycles are pretty common in nature. We've already seen a couple back when we talked about the acidity, the basicity of various amines, right? I think I pointed out pyridine and pyrrole as examples. Those were heterocycles where you've got a ring compound with a nitrogen present in it. So basically you'll see that in a lot of various molecules. All right, so I've pointed out pyrrole, for example, is an example of a heterocycle that's aromatic. Imidazole is another good example of a molecule that's a heterocycle. So if you notice again, we've got nitrogens that are part of our aromatic ring here that are actually it's kind of interesting here. This nitrogen contributes its lone pair towards the aromaticity. This one over here doesn't. This lone pair is actually much like that of the nitrogen here is much like that of pyridine, where that lone pair is not involved in making this ring aromatic. All right. You've probably heard of histamine. Histamine also has this imidazole system in there. Okay, I think we've already talked about pyridine. Again, pointing out that that lone pair is not necessary for meeting Huckel's rule. Okay, and so this affects the basicity of those nitrogens, right? If you look at the conjugate acid, the ammonium ions that are formed, pyridine has a significantly higher pKa than something like pyrrole, where not having that lone pair to meet Huckel's rule makes this very, very unstable, and therefore this really wants to give off its proton and go back to being the neutral pyrrole. But again, keep in mind that we still are dealing with an sp2 nitrogen, so compared to this sp3 nitrogen here, on our aliphatic, our regular amine, we have the resulting ammonium ion is much more stable and therefore has a much higher pKa. Okay, so pyrimidine is another example of a nitrogen heterocycle that's also aromatic. Again, just like pyridine, you have the ring is already meeting Huckel's rule. Those lone pairs are not involved in the resonance. Okay. And so let's talk a little bit about spectroscopy. We've seen how amines look like in IR spectra. So remember, they're going to show up, pretty downfield, like around that area where you see your OH stretches and things like that. If you recall, if you look for the number of stretches in this region, in this 3300, 3500 region, that can tell you the difference between a primary versus a secondary amine, right? So remember, you can have, a primary amine has 2 protons, right, on that nitrogen. So, you have your nitrogen, and it's got 2 hydrogens, right? There's a lone pair in this. So these 2 hydrogens can go, when they move in and out, against the nitrogen, when these bonds expand and contract, they can do it in sync, what we call a symmetrical stretch, or they can be asymmetrical, like this one comes in while this one goes out and vice versa. All right, and that's an asymmetrical stretch. And so as a result, we see 2 peaks, 2 signals in that region. In the case of a secondary amine, though, there is only one nitrogen-hydrogen bond. Okay, so this only moves back and forth, so we only see the single stretch for that. Okay, and obviously for a tertiary amine, there's no hydrogens, so you're not going to see any nitrogen-hydrogen signals. Okay. If you do have a tertiary amine, you can protonate that nitrogen and turn it into a corresponding ammonium salt. And of course, once you've protonated that nitrogen, it now does have a nitrogen-hydrogen bond. So that might be a good way to prove that you've got a tertiary amine. You can have a signal, not show up when it's neutral, but the signal will show up when it's protonated. With NMR spectra, your nitrogen protons your amine protons will show somewhere between zero point 0.5 and 5 ppm. That's not really very helpful because that's like half the spectrum there. So there's a lot of factors that can affect where your amine proton signal will show up. So that being said, because these protons will exchange, they're relatively labile, just like with alcohols or carboxylic acids. Instead of getting a nice sharp peak, you might get a very broad peak, and depending on the level of hydrogen bonding, it might disappear altogether. All right, so here we have, example molecule. We have, propylamine, or, propanamine, to use the IUPAC name there. You can see from the proximity to that electronegative nitrogen and the deshielding effect that, your protons on those carbons get shifted further and further downfield, and you have less of that deshielding effect as you get further away from that nitrogen. Okay, same thing with the carbon 13 signals. You can see that each of those carbons gets shifted further and further downfield as you get closer to the nitrogen. And as I pointed out with the amine protons, they can show up. There's a wide range where they'll show up. You might expect them to show up further downfield, being attached to that electronegative nitrogen, but here you can see these ones only show up at 1.2. Okay. With mass spec, if you remember towards the beginning of the semester, you probably noticed that amines or anything with a nitrogen tended to have an odd number for its the mass of its parent ion. This is just a quirk of the number of hydrogens needed to complete nitrogen's octet. So, if you have an odd number of nitrogens, you're going to have an odd number for your mass. Okay. All right. Of course, that's not just kind of a blanket statement, right? There's going to be a few exceptions. You've got to take into account isotope effects, but generally speaking, for the most common parent ion peaks, that's the case. Okay. Going back to that chapter on mass spec, I think back then we also talked a little bit about alpha cleavage. We pointed out, I think alcohols do this as well, but in that section, I think I would have also pointed out that amines can also do this. So in terms of how nitrogen-containing compounds can fragment when running a mass spec on them, typically you will get a fragment with the nitrogen of your amine, the alpha carbon, and anything that's attached to that. Basically you break a bond that's attached to that alpha carbon, and anything else that's on that alpha carbon will be included in that fragment, as you can see here. You can see that resulting fragment is resonance stabilized. All right, and that's it for this chapter. So, let's go through some practice problems, and of course, with the more practical stuff, procedural stuff, please, do check out the homework. Okay, so let's go ahead and name this amine that we have over here. You could probably, I was going to say you could use the common name, but I think the fact that we have a chlorobenzene here makes using the common name kind of weird. So, I would suggest trying to use the IUPAC name. Probably use the benzene as your parent, carbon-containing group. And, so I would use a root word of aniline and go from there. Okay, so if you've taken a stab at this, the answer is over here. So if you could imagine this being an NH2, this would be an aniline with a chlorine at the number 4 position, or a para position. And that nitrogen has substituents of a methyl group and a cyclopentyl group, and putting those in alphabetical order, that's how we would write that out. All right, here's a synthetic problem. So go ahead and predict the major product of this reaction after it goes through these synthetic steps. Okay, so probably notice that we have sodium cyanide. Cyanide being a very strong nucleophile is going to do an SN2 substitution. So again, like notice that they've given us stereochemistry of these, these carbons over here. These are actually both chiral centers, so something to keep in mind. But remember, with your SN2 mechanism, we actually have an inversion of stereochemistry, on that carbon where the bromine leaving group leaves. Okay, so you wind up having your nitrile group on that carbon, but it's pointing towards you, which is why eventually the amine that we're going to get when we reduce it in the next step has a solid wedge and not a dashed wedge. Okay, so here's a retrosynthetic problem. We're trying to make the secondary amine over here. See if you can think of a way to do that. Okay, so if you've taken a stab at that, let's go over the answer. So you can see here they've done a reductive amination. So here we've taken the one half of the molecule, or one part of the molecule, and we're basically just going to do an amination to change that into the corresponding imine, and then reduce it with sodium cyanoborohydride down to the resulting amine. Now, actually, I guess we're going to, since this is a secondary amine we're making, we would start off with a primary amine containing that functional group that we want on there. In this case, an ethyl group, or this alkyl group, I guess, not really a functional group per se. But yeah, that's it. Basically, you'd use this primary amine and do a reductive amination to get this secondary amine. Okay, so here we have a starting material. We have, benzene. So you want to go back to your EAS reactions, think about how you would add functional groups to this benzene, and then, get, basically converted in subsequent steps to this amide that we have over here. Okay, so if you pause this and come back, hopefully you realize, well, we probably have to start off with a nitro group of some sort. So your first step is going to be involve reacting this with concentrated nitric and sulfuric acid, and you go from there. So you take that, you reduce it using a metal and acid to the corresponding amine, and then we're just adding on this acyl group, right? So basically we reacted with a result. We've got effectively aniline after that second step, which is an amine. So that amine nucleophile is going to attack our acid chloride here and swap out the chlorine for that amine and make the resulting amide. All right, that's it for this chapter. So if you have any questions, as always, please let me know. And good luck on your quiz.